So we learned about two ways to charge objects, two ways to give an object either a negative charge or a positive charge, more electrons than protons or more protons than electrons. Those two ways were conduction and induction. One of these ways, either conduction or induction, never involves a transfer of charge. Can you tell me which one that is? Conduction or induction, that never involves the transfer of charge. Tristan? Good. Induction never involves a transfer of charge. Oops, I'm putting a letter Q there because I kind of forgot that you don't know what Q is yet, right? Q means charge. We're going to talk about that later on. I'm just going to abbreviate it that way right now, okay? Never a charge transfer. And it never involves touching. As opposed to conduction, which always involves a charge transfer. Now fill in the blank right here, blank touching. Usually involves touching, usually. Not always, but it usually involves touching. We talked yesterday about a couple examples where it doesn't involve touching, but it's kind of close to that. And we break conduction down into two subcategories. The first one, pretty easy actually, charging by friction. That simply involves rubbing two things together. When you rub two things together, let's say they start off neutral. They don't have to, but let's say they start off neutral. One of them is going to become positive, and one of them is going to become negative. Now, the one that becomes positive, what's happened to it? Hey, what's happened to it? What charge has been transferred when the object has become positive by rubbing two things together? It's lost electrons. Good. Hey, we're not going to gain protons. Okay, it doesn't gain protons to become positive. It loses electrons to become positive. Now, the other thing is going to become negative, right? The law of conservation of charge says charge can't be created or destroyed. So if something has lost electrons, the other thing has got to gain electrons. If something has become positive, then something else has to become negative. Let's say that we rub two things together, both plus 5. What do they become? Rub them together, they're going to become, one might be, no, rub them together, one might become plus 8, plus 9, plus 6. We don't know, right? Let's say it's plus 8. If they both start out as plus 5 and one of them becomes plus 8, then the other one is going to become what? Plus 2. Because the total amount of charge before we rub them together was plus 10. The total amount of charge after we rub them together must also be plus 10. Does that make sense? Okay, that's not charging by contact. That's not balancing them out, right? When we charge by contact, that's when we're trying to balance them out. When we're charging by friction, we're doing just the opposite. Question?
Does that transfer of charge happen when you rub any two objects?
No. Well, to some degree, yes, but not to a large degree. Not to a large degree. Some materials rubbing together, you don't get a dramatic transfer of charge at all. Okay. The more dissimilar the materials are, the more unlike they are, the more you tend to get a transfer of charge from one to the other. Some materials will give up electrons quite easily, and some materials will gain electrons quite easily. Some materials won't gain or give up electrons all that easily. Generally, again, if you rub two things together that are quite similar, you're going to get less of an effect, okay, than if you rub things. One of the examples, we used to do this little activity when I taught Science 9, back when we used to have grade 9 at the school, and we did electricity within the grade 9 unit. We used to do this little activity where we erased pop cans from the front of the room to the back of the room. And we did that by using static electricity. Basically, we took rabbit fur, or we took cotton or wool or something and rubbed it against a piece of plastic, or rubbed it against a piece of plexiglass or something like that. And then we literally used that charged object that we just created, not created, but you know what I mean, right? Transfer charge to, okay? This new charged object that was neutral before, and we put it nearby the neutral pop can, okay? And we attracted the pop can to it, okay? And the goal was to get your pop can to the back of the room first. Now, some materials worked way better than others. And one of the things that we found was, you guys know those plastic golf tubes you can buy, golf club tubes that you put in your golf bag? Okay, those plastic golf club tubes and rabbit fur worked incredibly well together. But then there was other materials that, you'd rub cotton with this, and you'd still transfer charge and it would become positive or negative, but wouldn't attract the pop can, so it wasn't that much of an effect at all. Some work way better than others. Everything's going to work to some degree, okay, but some work way better than others. Okay, charging by contact, we kind of already alluded to this, right? We talked certainly about it quite a bit yesterday. You touch two objects together, okay? Instead of rubbing two objects together, you're simply going to touch two objects together. The condition on this one is that they must be different charges to begin with, because if they're the same charge, you get no net effect. Let's say we have +5 again. +5 and +5, touch them together, what do they balance out to be? +5 and +5, right? You might get some electrons transferring in that process, but there's no net transfer of charge. In other words, if one goes one way, you're probably going to get one going the other way, randomly, okay? If you want to transfer charge, a net transfer of charge from one to the other, then one of them is going to be +5 and one of them is going to be +7. What are they going to balance out to be when you touch those two objects together, assuming they're roughly equal size and roughly equal shape, and that they're conductors? +6 and +6, right? 5 and 7 were 12. Okay, 6 and 6 is 12. Here's a tougher one for you. What if you had -2 and +12? -2 and +12. What are they going to balance it to be? What's the total charge, first of all, between those two? -2 and +12. Total charge is +10, right? So what's it going to balance it to be when we touch those two objects together? +5 and +5. Good? How about this one? How about this one? +5, +10, +15. Let's say we touch them all together at the same time. +5, +10, +15. What are they going to balance it to be? +10, +10, and +10. Okay, 5 + 10 + 15 is equal to 30. Divide it by 3 this time. Instead of dividing it by 2, we get +10. Now, that's not like the question we did yesterday, right? What's different about it? This time, they all touch at the same time. Yesterday, object 1 touched object 2, and then object 1 touched object 3 after they were separated. So be careful about the difference there. If they touch at the same time, add them up and divide by the number of charges you have. If they're stages, like it was yesterday, then treat them independently. Treat each step as a separate problem. Okay, let's go now to induction, specifically the temporary separation of charge. I'll draw the picture that we drew yesterday here. We've got a neutral object here, and we're going to bring a negatively charged object nearby that neutral object. What's going to happen to the protons in that neutral object when I bring that negative object nearby? Yep. They're going to stay where they are. The protons, if it's a solid, the positives are always going to stay where they are. Even if it's a liquid or a gas, the protons will, but you can have positive ions that move around within a solid or a liquid. Sorry, a liquid or a gas. The protons are always going to stay where they are. What's going to happen to the electrons in this in this solid here? Okay? Yeah, they're going to be pushed away to the left. They're repelled by the negatively charged object. So now we got these electrons over here. Now we still have a neutral object, 3 positives and 3 negatives. But we have a separation of charge, the left side being negative and the right side being positive. By the way, I drew all 3 of those electrons going to the left side. Do they all go to the far side? No. No, but enough of them will go to the far side to still create this effect of one side being positive, one side being negative, a separation of charge. Why do we call it a temporary separation of charge? What's the deal with that? Why don't we just say a charge separation? Yeah. Good. Good. Those negatives, those green negatives would just go back more or less to where they were before if I took away that charging object. Okay, so it's a temporary separation of charge. Let's draw one more picture for this now. This time let's draw a neutral object again. And let's draw a positively charged object this time that's nearby it. What's going to happen to the protons, Adam? No. What's going to happen to the protons, Tristan? Nothing. Protons stay where they are, right? What's going to happen to the electrons, Adam? Good. They're pulled towards the positively charged object right here. So they're going to come over, at least some of them are going to come over to this side. Positive side, negative side. Again, a temporary separation of charge. What do you notice? You look at both of these diagrams. What do you notice about the side that's closest to the charging object? Okay, this is my charging object. This is my charging object. What do you notice about the side of the neutral object that's closest to the charging object and the charging object itself? What do you notice about those? Okay? It's always opposite, yeah. So the positive side will be closest to the negative. The negative side will be closest to the positive. That's why charged objects attract neutral objects. Remember that third law? It's not positive attracts neutral. Charged objects attract neutral objects. We have to have a temporary separation of charge there. Okay, we have to. That's why protons don't attract neutrons. You can't get a temporary separation of charge in a neutron when a neutron isn't made up of protons and electrons. So a negatively charged balloon will attract the neutral wall, okay, but a negatively charged electron will not attract a neutral neutron because you can't get a temporary separation of charge. All right, how do I make it permanent? We get the first scenario again, negatively charged object. How do I make this permanent? How do I get a permanent charge here, Matt? Yeah. Okay. Does that grounding wire, by the way, have to be literally a wire? No. No, I mean, a lot of times it is, right? But it doesn't have to be a wire. Okay, we gave you the example yesterday of when I was the grounding wire, right, between the fridge and the stove, carrying the electrons, the excess electrons from the fridge to the stove into the ground. Okay, it can be a wire, it can be any kind of conductor, okay, that directs electrons, that provides a path from something into the ground. So where do these protons go in this neutral object here? Nowhere. Where do the electrons go? They're going to get pushed to the left side here, right? Pushed away to the left side. That creates, if we don't have the ground wire there, a temporary separation of charge. But now we do have the ground wire, or something at least that connects it to the ground. Where do they go from here? They go into the ground, right? So let's take those three negative charges, drive them down into the ground. We're now left with a positive charge right here. What happens when I take away this negatively charged object right here? They're going to go back, right? Because now we got a positively charged object, a neutral ground. The electrons are just going to come right back to more or less where they were before, and it's still going to be a neutral object. Okay? But if I cut this ground wire before I take that object away, then the electrons, although they might want to come back, have no way of getting back. What if we change this around just a little bit? What if we take the ground wire off here? Let's add our electrons back in here. And let's add our ground wire over here now, on the right-hand side, close to the negatively charged object. What's going to happen to them now? Protons are going to stay where they are, right? The electrons are going to be pushed to the left? No, they won't be pushed to the left. Yeah, well, let's assume that the object is stationary, yeah. The electrons are going to be pushed as far away from the negatively charged object as they can go. Okay, so where are they going to go? Not to the left-hand side of the neutral object. They're going to go out of the neutral object. It doesn't matter where the ground wire is. They're going to be pushed through that ground wire down into the ground, leaving you with a positively charged object. Okay, we're going to cut that ground wire the same as we did before, and we're going to be left with the same effect. What if we did this? Let's change it a little bit more here. Let's put our negatives back in there again, evenly distributed, and start again. Now we've got some other big object. Okay, it's not the Earth, but it's something that's big, and that can take a lot of electrons or give away a lot of electrons, depending upon what it needs to do. I touch it to this neutral object. Where are the electrons going to go now? It's exactly what's going to happen. They're going to jump ship. They're going to go over here into this object. We're left with a positively charged object again. Is it permanent? Almost, but not quite. What if we take this negatively charged? There we go. Now it's good. What if we take that negatively charged object away? Those electrons are going to go back to where they came from before. So what do we got to do? What do we got to do before we take that negatively charged object away? Let's take away the green object, or separate the green object from the neutral object. And that way the electrons have no way of getting back. We'll assume that they're not going to jump to that side, right? That wouldn't be induction, then that would be a conduction taking place then. What do we call this? Is this still induction? We had a transfer of charge, but the overall process is still called induction because the thing that's doing the charging is not touching and it's not transferring charge. This green object here, whatever it is that not effectively the same thing as grounding the object? Yeah, so it's not the earth, but we're doing the same thing, so we might as well call it grounding. It's exactly the same thing. Okay, instead of attaching a wire to the earth, we're attaching another really big object which serves the same purpose as the earth serves when it's attached via a wire. All right? Got a couple examples, illustrations to show you here. Neither of the ones that I want to show you here, you have to copy down. Neither of these are direct curriculum objectives. Neither of these will likely be asked on a test or an exam, although you never know. Okay, what we have to learn in Physics 30 is what we've just learned. Okay, all of this stuff, the table. When I was in grade 12, okay, we might have been asked a question like, describe the difference between induction and conduction, or list the 4 ways of charging objects, or whatever, right? That's the kind of things we were asked. Now you guys are asked to explain how this works when you've never seen it before. Okay. The odds of you seeing this exact example are slim to none, although it could happen. Okay, the odds of you seeing some other example where you have to interpret a little bit are probably pretty high. Okay, we'll go through a couple examples. Okay, the idea there is that hopefully after we go through a couple examples, you'll be better equipped to analyze a novel situation yourself, even when you've never seen before, okay? This is what we call an electrostatic precipitator. It's an air cleaner, basically. It serves the same purpose as your furnace filter serves, although it does it in a slightly different way. You put your furnace filter inside your furnace, right? As the air goes through, it filters out all the dust, or not all the dust, but a lot of the dust out of the air. But it does it mechanically, okay? Pieces of dust above a certain size can't physically pass through the filter. So they don't go through the filter, and then the air that comes up through your vents is cleaner because some of that dust was filtered out. Okay, this filters out more of the dust. Here's the air. These wide wavy lines are the air. These little circles inside the air represent little dust particles. Those dust particles are normally neutral particles. So we've got neutral dust particles inside this air that's being pushed through this electrostatic precipitator here. Now, these blue rods sticking up, I don't know if you can see the little negative signs on them, but they're supposed to be negatively charged. They're negatively charged because they're attached to the negative side of a battery. Now, when that air and those neutral dust particles go through and touch these negatively charged rods, what's going to happen to them? They become negative. What do we call that? Charging by what? Charging by conduction. The neutral dust particles touch the negative rods. The neutral dust particles try to balance out. They're not going to balance because they're not same size, same shape, right? But they're going to try to balance. Bottom line is they're going to become negatively charged by conduction, specifically charging by contact. Now we've got air with negatively charged dust particles in it. The air with the negatively charged dust particles keeps going through these plates, these red plates. These red plates that are attached to the positive side of a battery. These plates are now positive. What's going to happen when these negatively charged dust particles pass in between these positively charged plates, Chad? They're going to be attracted to the plates. So now you've got these negatively charged dust particles that are pulled over towards the plates. Okay, they stick onto the plates. The air just keeps on going, and then the air that comes out the other side is what? Clear of dust, more or less, at least clear of dust. So we charge the dust particles negatively so that they're going to be attracted better to the positively charged plates, and then the air just goes out the other side relatively clean. Yep. That's a good point. Yeah, that's a good point. First of all, the question, if you didn't hear it, was, aren't some of those dust particles not going to touch the negatively charged rods there and therefore not going to become negatively charged? Yeah, you're probably right about that. But there's a couple of things that come into play there. First of all, if this negatively charged dust particle it's become negative because it's touched a rod there, and this one hasn't touched a rod, so it's neutral. Well, maybe this neutral one touches this negative one, and it gains a charge from another dust particle. The second thing is, these plates are positively charged. The positively charged plates will attract neutral dust particles. It's just going to attract positively charged or negatively charged dust particles better. Does that make sense? Okay, so, and we're not suggesting that you're going to get completely pure air through the other side as well. You're going to get some dust going through the other side as well, but it's a more effective technique than it is just by using a regular furnace filter, if that makes sense. Here's another one. We're painting a fence. But you know what? We want to paint this fence. You start looking at the implications of this. First of all, I don't want to paint it with a brush because it's going to take too long. Plus, I don't like the look of when you paint it with a brush, right? You can see the brush marks and whatever. So I want to spray it. But the problem with spraying this is that my swimming pool, not my swimming pool, say it's my swimming pool. I don't know why I need a swimming pool because I live on the ocean there. But anyways, yeah. Yeah, the first world problem is that I have a swimming pool on the ocean and I need to paint my fence. Yeah, could be. Yeah, could be. Sharks. That's what it is. So I want to paint my fence, but I want to spray it as opposed to use a paintbrush because it doesn't need a job. The problem with that is that there's going to be a lot of overspray here, right? And I can't cover up everything. I can't cover up my entire pool, and I can't cover up the deck and all that stuff. So what am I going to do so I don't make a mess of the deck and I don't make a mess of the pool itself and contaminate the water with all this paint, whatever? I'm going to use, go ahead. Yeah. I'm going to use an electrostatic painter, okay, an electrostatic paint sprayer. What I'm going to do first is make sure that this is grounded, make sure this fence is grounded, okay. Normally, this fence is probably going to be grounded automatically because it's going to be in the ground, right? Okay, but if it's, let's say, for whatever reason, somehow insulated from the ground, okay, then then we're going to want to make sure that we've got it connected to the ground via a ground wire of some type. Next, we're going to use this electrostatic sprayer, which has inside it this rod that's either positively charged or negatively charged. Doesn't really matter which. Let's make it positive. Okay. We take the paint from the paint can. We use a compressor to blow the paint up through the sprayer. And as it goes through the sprayer, this neutral paint touches this positively charged nozzle. What happens to the paint particles now as it leaves the nozzle? They become positively charged. So now I've got a whole bunch of positively charged paint particles. Now those positively charged paint particles are going to be attracted to the metal fence. They're going to be attracted to anything that's neutral, but they're going to be attracted particularly to the metal fence because first of all, it's a conductor, and second of all, it's grounded. So basically there's a source and a sink, an infinite source and a sink of electrons through this ground. So they're going to be more attracted to the fence than they are anything else. So I blow it towards the fence. Good. Spray the front of the fence. Works great. Are all the particles of paint going to touch the front of the fence? Probably not, because some of them are going to be moving a little bit too fast. Some of them are going to be going in between and go right through, right? What happens to those particles? Well, because they're positively charged, and this thing is neutral, and it's attached to the ground, these positively charged paint particles that are going around the back are going to be pulled back to the back of the fence. So instead of getting overspray on the concrete deck of my lovely pool beside the ocean, what I'm going to get is, I'm going to kind of kill two birds with one stone. No overspray, and we're going to paint the back of the fence at the same time. It's a really, really clean process with very little overspray. Yeah, it works very well. Yeah, it does. Yes, yes. They'll do that when they're painting cars in a factory. Actually, is use electrostatic spraying, and the reason for that is not so much overspray, and not so much like we don't want to get the walls dirty, right? In the factory, the paint part of the factory, but rather, and they don't. It's faster and it's a lot less wastage, right? Like they don't waste nearly as much paint that way, so it becomes cheaper. If you save $20 a car, it's $20 a car, right? When you produce 1 million cars. Sorry? Does that make sense, guys? So there's a million applications of what we've been talking about, charging by conduction, charging by induction, and so on. Okay, here's a couple. Okay, there's a million more. The odds of you seeing these two on an exam, okay, are small, but not zero. The odds of you seeing something on an exam where you have to interpret, probably fairly high, but you can do that. None of these are all that hard, right? Okay, all we have to know is the basic rules, the basic laws of electricity, and we're good. Wilson? Yeah, no, that's a good question, Wilson. It wouldn't be a simple matter of, just stand in front of the fence and just spray it. You probably have to go behind the fence as well to make sure you had an even coat. Okay, but certainly, yeah, and I don't think, I don't know for sure, Wilson, on that. I'm not a professional painter, but I don't think you'd get, if you just stood in front of that fence rod there, I don't think you'd get as much coverage on the back as you would on the front. So I think you'd have to go around to the other side as well, right? But the point is that it's at least partially covered, okay? Partially covered, plus you haven't wasted all that paint. It's actually going on it, so that when you do go to the other side, you won't have to paint quite as much. You won't have to do as much. Okay, let's take a look at a couple multiple choice questions here now. Multiple choice 37 and 38 at the end of your Unit 2 section in your worksheet booklet, okay? Submit these, please, as multiple choice number 1 and 2. Okay, let's take a look here. 37, 79% of you said A. Okay, 21% of you said C. The bottom of a thundercloud usually becomes negatively charged before the lightning strikes. So here you get this negative charge right here, okay, which is closest to the ground, obviously. Before the lightning strikes, the charge of the ground directly beneath the thundercloud will become what? Positive by induction or positive by conduction? Okay, I'm happy to see that everybody in the class said that the ground would become positive, or the ground directly beneath the cloud will become positive. The rest of the ground, who knows, right? But this part of it becomes positive. Everybody said that. That's good. Now, the only question is it induction or is it conduction? The answer is induction. It is A. Okay, and the reason it's A is because there's nothing being transferred before the lightning strikes. There's a separation of charge produced in the earth. A negative object will push the negatives that were near the surface of the earth down into the earth, so that the surface of the earth nearest the cloud becomes positively charged. Does that make sense? That's induction. There's no transfer of charge. There's no touching going on there. That's induction. Anybody want to volunteer why they said conduction? Any of the 21% of you that got that wrong? No? All right. 38. During the downward strike, the charge on the top of the tree becomes what? Well, now the lightning strike comes from this cloud that has a negative charge at the bottom of it. That's going to transfer negatives downwards here. The top of the cloud is going to become, the top of the tree is going to become negatively charged, right? So that leaves us with either A or B. Now, 79% of you said B. 21% of you said D. Okay. Now, let's be optimists here. Okay. I'm happy that all of you recognized that it's conduction. Okay. In the end, charge is being transferred from the cloud to the tree. That's got to be conduction. So everybody got that. Okay, now some people got a little bit confused between whether it's negative or neutral. Okay, we say it's negative because these electrons are going down towards the tree, and as they're striking the tree, the top of that tree gains negatives. If it gains negatives, it has to become negative.
So when the bottom of the cloud is negative,
Yep,
through induction, it makes the ground positive.
that's right.
Why wouldn't it make the tree positive in that same process?
It would, but during the strike, there's negatives being transferred down in there too.
So if it was positive, and then you're adding negative, would it technically go to neutral?
No, because, I mean, when you're transferring negatives, a massive amount of negative charges down there, okay, it's going to be overwhelmingly negatively charged, okay? By that rationale, okay, you could stand there on the ground just before lightning's about to strike you, you would have a charge separation induced in you. Then when lightning strikes you, you become neutral, you're fine, right? Does that make sense? I know. Yeah. So it does become negatively charged because of that massive amount of negative charge that's coming down. I know what you're saying there. I know what you're saying, but
Like I'm thinking, like I was thinking, like the tree is kind of sort of acting as almost a wire, and the electrons going straight from the cloud
yeah,
into the ground.
yeah. Nothing really happens to the tree.
Except the flow of the light.
Well, you get the flow of electrons through, right?
Yeah.
Which
Yeah. Because the flow of electrons through it, but I was thinking they flow through it.
yeah.
They don't stay.
Well, regardless. Well, wait a second. Not at the end. Let's not worry about the end, okay? Because it says during the lightning strike, right? During the lightning strike. Let's not concern ourselves with down the road. Let's concern ourselves with what it says. During the lightning strike, okay, there's a massive amount of electrons being added to this tree. It's going to become negatively charged. I remember years ago I was whitewater rafting with my wife. We didn't have any kids at the time. We're in Kananaskis country, and it's a nice day, and then it starts clouding over, then it starts raining, and then it starts thundering and lightning. So we're in the middle of the Kananaskis River, okay, in the middle of nowhere, rafting down this river, and there's a lightning storm going on. And I remember at the time, the guide said, you know, we probably should get off the river here, which is probably a wise thing to do, get off the water in a lightning storm. So we get off the river, and he says, let's all come over into the trees here, and you know, we'll kind of wait out the storm. And I'm like, no, I don't think I want to do that. So my wife and I, we're the only ones kind of just sitting in the open, kind of in this little open field in front of the trees beside the water, as everyone else thinks like these guys are crazy. Okay? Why did I not want to go in the trees in the event of a lightning storm? Lightning hits the tallest things, not the short things. Hey, lightning hits the trees. Oh, wait, that should protect us, right? Because if lightning's going to hit the tree, it's not going to hit me, right? The problem is, you know that more people are actually killed, and as much as you're probably going to laugh here, it sounds silly, but more people are killed by exploding trees in lightning storms than they are by actually being struck by lightning, okay? Lightning strikes a tree, and what happens? What's a tree mostly made out of? What's any living thing mostly made out of? Water, right? What happens to water when you've got several million volts going through it? It heats up, it boils, and it turns to steam. What happens to steam? It expands, right? And what happens when it's in this enclosed container like a tree? It explodes. It explodes. Now, that didn't happen to anybody, but in the end, I wasn't willing to take that chance. If you're in the middle of a field, you're actually, as long as you make yourself relatively small in the middle of that field, you're relatively safe. I wouldn't want to say safe, but relatively speaking, you're safe because lightning wants to take the easiest path, and normally the easiest path will be the tallest thing. That's why we have lightning rods on the top of tall buildings, right? To encourage lightning to strike there as opposed to strike somewhere else on the building to do damage. Okay, make sense? You're out on a golf course golfing, and there's a lightning storm. What do? Well, I'll tell you one thing not to do. Don't stick your metal golf club up into the air and make yourself, Carbon's a pretty good conductor too, though. So don't stick your carbon golf club up into the air. That would be good. So what should you do? Well, if you can get to a safe cover, like inside a building or something, then that's the thing to do, right? But if you can't, what should you do? Should you hide under that tree over there? Absolutely not. You should, if you can find a dip in the ground, like this. Yeah, seriously, go in a bunker, right? Go in here, sit down, make yourself small, put your hands over your head and make yourself into a ball. As silly as that sounds, lightning is a lot less likely to strike you down here when you're curled up into a ball than it is when you're standing up here, or even worse, when you're standing under that tree trying to stay dry. And drop the metal golf clubs. Don't hold on to those. The thing that you see on the board right now is called an electroscope. This is a device that detects charge. Doesn't tell you what kind of charge you have. Doesn't tell you how much charge you have. It just detects the presence of charge. You either have charge there, positive, negative, certain amount, whatever, or you don't have charge. We've got an electroscope that looks like this. There's two forms of the electroscope that you see on the board right now. Okay? They're more or less the same thing. They just look a little bit different. We've got a few of these in the back there, but they don't work very well, so there's not really much point in bringing it out. What this consists of is basically an Erlenmeyer flask with a rubber stopper in the top. Okay? Inside that rubber stopper is a metal rod sticking down. Attached to it is a metal ball at the top, so all conductors, and then metal foil leaves at the bottom. Really, really thin pieces of metal foil, much, much thinner than aluminum foil. Okay, so thin that, in fact, before you handle these things and before you connect these things to the metal rod, you have to dry your fingers off. The sweat on your fingers is enough to cause them to stick to your fingers and rip them apart. That's how thin these pieces of foil are. They're very, very thin and very, very light. Okay, we want them to be very light so that you can notice the effect caused by electrostatic forces. Now here's what happens. These things normally are all neutral, right? Okay, the ball is neutral. It's got 4 positives, it's got 4 negatives. Okay, the rod is neutral. The leaves are both neutral. Okay, everything's neutral. When I bring let's say a negatively charged rod or a negatively charged object nearby, something's going to happen. The protons are going to do what? The protons inside this electroscope do what? They stay where they are. Don't go anywhere, right? The electrons will do what? The electrons are going to be pushed away. So let's take these electrons up here that were in this ball, and now let's push them down as far away as they can go. Some of them go this way, some of them go this way. The ball becomes positively charged because the negatives were pushed out. The leaves that were neutral have now become what? Negative and negative. What happens to these two leaves now? They repel each other and they push each other apart. So the leaves now spread apart. If the leaves spread apart, that tells you that charge must have been present in this object that was doing the charging. Now, if we switch that object to a positive object, how's that going to change things? Once again, we have a neutral ball up here, a neutral rod there, 2 neutral leaves. We bring a positively charged object nearby. Now the protons are going to stay where they are. The electrons are going to, yep, good. The electrons are going to be pulled up. So now these guys are going up here. Now the ball of the electroscope is now negatively charged and the leaves are positively charged. What happens to the leaves? They spread apart the same as they did when they were negative. So it doesn't tell us what kind of charge is there. If they spread apart, it just tells us that there is charge there. Okay? What if I did this? What if I did this? Yep. No. The electrons won't go into the ground. Yep. It's going to take electrons from the ground, right? So you're going to add a whole bunch of electrons into this system, right? Okay. So in the end, this is going to be a lot more negatively charged, but some of those negatives are going to be pushed down here as well, and ultimately probably make this whole thing negatively charged, including the leaves, right? Make sense? Good. Okay, got a few questions for you to work on for homework here. I want you to please take a look at page 523. And I want you to do, please, questions 6 to 10 for homework. Page 523, questions 6 to 10. I got one more multiple choice question that I want to go over with you. 6 to 10. Yeah, 6 to 10. One more multiple choice question that I want to go over with you. If you finish that up early, then we can have a couple minutes to work on these questions, okay? Last one that I want you to do is multiple choice number 36, please. You can submit that, please, as multiple choice number 1. Let's take a look here, everyone. It says a student places a positively charged sphere near a metal rod. Okay, metal rod's a conductor, so electrons can transfer if they have to. Both are on insulated stands, and the rod is grounded. They're on insulated stands. They're telling us that they're on insulated stands, these things right here, so that we know there's no transfer of electrons this way. Okay? We know that basically being on the ground would have nothing to do with it. Although side Y is grounded here, so it is attached to the ground there. Provides a path for electrons to go one way or the other. We want to know the distribution of charge on the rod. Looks like they all have to do with end X. So what's going to happen to end X? It's a positively charged object that we bring nearby here. Something's going to happen to electrons, and something's going to happen relative to the ground. Are those electrons going to go down into the ground, or are they going to come up from the ground? They're going to come up from the ground, right? Because they're attracted to the positive. So that means they're going to come onto the rod from the ground. So that's either C or D. Now, if you're pulling electrons up from the ground, pulling negatives up from the ground, what does the neutral thing become? Negative. You're adding negatives to it, it becomes negative. Not just side X, but the whole thing here. So in the end here, the answer would be D, which 79% of you said. It becomes negative at end X, and that's because the electrons are moving onto the rod from the ground. Make sense? Good. All right, you got a minute or two here. You can work on those homework questions if you want, or you can pack it up and just finish them up for homework.